Okay, guys, 2025 Fall Probe 1. Um, Questions 6 through 10. Let's just get started. So, question 6, how many real solutions are there to the equation the absolute value of x squared minus 9 equals the absolute value of 2x plus 6? Okay, so there are multiple ways to do this, obviously. You could do the casework where you first do the case where x squared minus 9 is greater than 0. You do the cases where it's negative, so where it's less than 0, and then the same thing on the right hand side. So that's going to be 4 cases because we're either flipping or not flipping each. Actually, the cases where they're both negative, we're going to get a redundant well, this is a little bit confusing for me, so the way that I would do this is just graph it out. So x squared minus 9, that's going to be negative 3, and 3 are the roots of that. So it's going to look like that. But since it's the absolute value, we're not going to go into the negatives. We're going to have to flip all those negative values to positive ones. So it's going to look like that. And then this is going to be at 0. That's going to be the peak at 9. Cool. And then our line is going to start at 6. So let's say it starts right there. And then it's as a slope of 2. And then when is it going to hit the x-axis? It's going to hit the x-axis when x equals negative 3. So it's going to be like that. Okay, so we've already got a pretty good idea of what's going on here. We know that it has to intersect our parabola right here because they're both equal to 0 at x equals negative 3. So that's one intersection. And then we've got this other one where we're sort of projecting into the first quadrant, and then we're going to keep going and eventually hit the parabola again. So that gives us 3 real solutions because this is the real plane, the real Cartesian plane. Okay, circle C is inscribed in a 2x2 square. Okay, this is exactly the kind of problem that you need to get right, geometry-wise. So we've got a circle. It's in there like that. It's a bad diagram. It has to be inscribed, meaning it's touching all these little edges. Okay, well, that's good enough. What's the largest circle D that we can fit between the circle and the square? Okay, so this is C, and this is D. Let's put it right there. And we want to make it as large as possible, so it's going to be snugly fit, meaning it's touching all these points. And if we zoom in over there, it's going to be like this, sort of. And it's going to be touching. So the reason I'm drawing these radii is because, first of all, it's going to connect with this radius right here of circle C. And then also because it makes right angles wherever it intersects a perpendicular. So the radius of C, what would that be? Well, the diameter is just going to be the length of the square, side length of the square, which is 2. So half of that would be a radius, which is 1. So, that's equal to 1. And then this whole, if we look at this whole distance from the center of C to the corner, that's going to be 1 times the square root of 2, since it makes an isosceles right triangle right here. So we multiply by square root of 2. That's a special right triangle, 45, 45, 90. And let's just give this little radius that we're trying to find name r. So r would be right there. And then again, we can connect like this, right? And if you notice, r right here, we can move over here. So now we've got this, another 45, 45, 90 special right triangle. So this would also be r times root 2. We'd multiply it by root 2. So if we look at this, it's going to be from C to the corner, from the center of C to the corner. But we know what that length is. We know that it's equal to the square root of 2. Okay, but we also know that it's equal to 1 plus r times the square root of 2. So 1 plus, let's factor out r here. 1 plus the square root of 2. And then this is going to be the square root of 2 minus 1, and I'm going to subtract 1 on both sides so that we're left with just r on this side after we divide by 1 plus root 2, because we're trying to find r. So this means r is equal to the square root of 2 minus 1 divided by 1 plus the square root of 2. So if you don't know how to rationalize the denominators of a fraction like this, then the way you do it, basically whenever you see a fraction and you've got something, and then you've got like a plus b root c, then you're going to multiply by this fraction, which is just 1. You're going to multiply by a minus b root c on the top and bottom, right? Because when you do that in the bottom, you're going to get a squared minus b squared times c, if you know the difference of squares formula, which you should. And then the top, you're going to a times a minus b root c. Whatever a is doesn't matter. You just want to make sure the denominator is rationalized. Okay. So if we rationalize the square root of 2 minus 1 divided by 1 plus the square root of 2, we would have to multiply by 1 minus the square root of 2 on the top and bottom. Okay, and that's going to get us, well, let's multiply the top first. We have the square root of 2, and then we have plus or minus 2, and then we have minus 1 plus the square root of 2. Okay, and in the bottom, we're going to use the difference of squares to get 1 minus 2. So this is going to be 2 times the square root of 2 minus 3 over negative 1, which is also equal to 3 minus 2 times the square root of 2, which is d. So there's our answer. Okay, number 8. How many integers between 1,000 and 9,999 contain exactly 1 3 and 1 7 in their digits? Okay, so I wish this was a different kind of problem. I wish it was the integers from 0 to 9,999. Because if it was that, then we could treat every digit spot like an empty box and we could treat them all equally, right? We could say, you know, we have 4 options to put our 3. We have 4 options to put our 1 3. And then we have 3 remaining options to put our 1 7. And then we can use any digit from 0 to 9 except for 3 and 7, right? So we would only have 10 originally, but subtract that, we have 8. So we've got 8 options for the other 2 digits, right? So we included integers from 0 to 1000 that we shouldn't have. We should be ignoring the ones from 0 to 9999, right? Because those ones are not allowed, because it specifically states integers from 1000 to 9999. So we know that we included more and got 748. So if we need to get rid of some of the ones that we already counted, then there's no way that the answer can be greater than 748, right? So because of that, we can eliminate D and we can eliminate E. Okay. Now we need to figure out how many integers between 0 and 999 we counted. Like, how many were we off by? Well, luckily for us, it's the same situation we had before when counting, right? Except with 3 digits instead. So now we have 3 digits that could be our 13, and we have 2 digits that could be our 17, and then we have 8 choices left for whatever the last digit is. And that covers everything from 0 to 999, right? Because it counts when the first digit is 0. 6 times 8, which is 48. So we know that we counted, so we know we were off by 48, right? We counted 48 too many. So originally we had 768, but we need to get rid of the 48 that don't actually work, right? The ones that are too small. They're not within that 1000 to 9999 bound. So if we subtract those, we get a total of 720, which is C. Cool. Okay, so consider a right triangle and the length of its 3 sides. These lengths add to 18, and the squares of these lengths add to 128. What is the area of the triangle? Okay, so we've got our right triangle. It's an arbitrary right triangle, so let's just label the legs A and B, right? Because that's usually how you label right triangles, like the Pythagorean theorem. Speaking of the Pythagorean theorem, we can already figure out what the hypotenuse is just based on this, right? C squared equals A squared plus B squared. So if we square root this expression, we get C equals the square root of A squared plus B squared. So let's just label it like that, since we don't want to add another variable when we don't have to. So it's like this. Okay, cool. So what did it tell us about these lengths? It said they add to 18. So that means A plus B plus the square root of A squared plus B squared equals 18. And the squares of these lengths add to 128. Okay, so A squared plus B squared plus the square root of A squared plus B squared squared equals 128. So if you get rid of that radical, because we know that A squared plus B squared has to be positive, then we're going to get A squared plus B squared plus A squared plus B squared again equals 128. And I could combine those into like terms, but I could also just divide everything by 2, because notice that there are 2 A squareds and 2 B squareds. So let's just divide everything by 2. So we get 64 equals A squared plus B squared. But we already saw A squared plus B squared before, right? We know that it appears in this equation right here, A plus B plus the square root of A squared plus B squared equals 18. Okay, so let's figure this out. A plus B plus, now let's substitute in 64. The square root of 64 equals 18. The square root of 64 is 8, right? So it's the same thing as saying this. A plus B plus 8 equals 18. That means A plus B equals 10. So if you have the sum of the squares of A and B, and you have the sum of A and B, then you can figure out their product, and hence the area afterward, by doing this. Okay, so the area of this triangle is going to be 1/2 a times b, right? So that's what we're looking for. We're trying to find 1/2 a times b. So if we take a plus b equals 10 and we square it, then we get a squared plus 2ab plus b squared equals 100. Okay, where was I? Hello? Oh yeah. So a plus b quantity squared to get a squared plus 2ab plus b squared equals 100, but we already have a squared plus b squared. That's 64, so we have 64 plus 2ab equals 100. 2ab equals 100. So then 2ab would be equal to 100 minus 64, which is 36. So ab over 2, which is what we're looking for, if you remember, is going to be 18 over 2, which is 9, not 18. It's 9. So, yeah, boom. The area of that triangle is 9. Okay. Nice. Question 10. AAA batteries can be purchased in packs of 4, 10, and 15. Which of the following is closest to the largest number of AAA batteries you cannot exactly buy? So this one's actually kind of a pain. The best way to do it is notice that if some number can be made, so if you can make n, then you can also make n plus 4, right? If n, then n plus 4. Let's just say n implies n plus 4. And what I mean by n implies n plus 4 is that if n works, then n plus 4 works. So notice that a number can be 0 more than a multiple of 4, 1 more than a multiple of 4, 2 more than a multiple of 4, or 3 more than a multiple of 4, and that being 4 more than a multiple of 4 is the same as being 0 more than a multiple of 4. So this is actually called modular arithmetic, is when you reduce a number to a property like this. So we would say we're taking this mod 4. So if we take 30 mod 4, then we're saying, okay, how much more is 30 than a multiple of 4? And 28 is a multiple of 4, so it's 2 more. So we would write 3 lines for equals, which means congruent. So we would say 30 is congruent to 2 mod 4, which is just saying that it has remainder 2 when divided by 4. It's just another way of saying that. So if we find a number with that we can make that's 0 more than a multiple of 4, then any number that's also 0 more than a multiple of 4 that's greater than that number, we can also make. So what that means is 4 we can make, right? Since we can just buy a pack of 4, right? But that also means that we can make 8, because we're adding 4. We can make 12, 16, 20, forever, right? Okay. Now, how about this? I'll write it over here. We can make 4, so we can make 8, 12, 16, 20, 24, etc. Okay. So, how about 5? Wait a second. Yeah, you can't make 5, right? So 5 doesn't work, but we can get bigger than that. 9. You can't make 9, right? There's no way to combine 4, 10, and 15 to get 9. So if you think about 10, right, we can buy a pack of 10, right? So 10 is congruent to 2 mod 4. I'll cross out 0 because we've already eliminated everything that's congruent to 0 mod 4. So now we're at 10, okay? And that means that 14 we can make, 18 we can make, 22 we can make, 26 we can make. And then anything after that we can also make, right? So 30, 34, etc. Now 15 we can also make by buying a pack of 15, right? 15 is 3 more than a multiple of 4. So we got rid of 2, we got rid of 3. 3 more than a multiple of 4 is 15. So if we make 15, then we can make 19 by buying another pack of 4, and then 23, and then 27, and then 31, and so on. Okay, but now we need one mod 4. Okay. How do we get that? What's the smallest way we could do it? Let's just think of multiples of 4. 4, 8, 12. Okay, if we add 1 to these, 5 we can't make, 9 we can't make, 13 we can't make, 17 we can't make, 21 we can't make, 25 we can make, right? Because if we have a pack of 10 and a pack of 15, then we can make 25, right? So if we make 25, then we can make 29, and then we can make 33, and then we can make every number after that, right? Because we're filling in the gaps before, right? We have 24, 25, 26, 27, and then we're going to have 28, 29, 30, 31, right? Because next is going to be 30, next is going to be 28, and then we have 31 and 33. We have 29 and 31, sorry. So what's the largest number that we didn't write down? Did we write down here? We can organize it like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, ... So I'm going to circle the ones that we can make. We can make 4, 8, 12, all these we can make, right? This whole row we can make, because these are the 0 mod 4, right? We can make here we got to go another row, 25. We can make all those, right? We can make everything past 25. We can make everything past 10, and we can make everything past 15, right? So which of these numbers is biggest that we didn't circle? It would be this one right here, 21. So 21 is the largest number that we can't make, because these are all the numbers we can't make, is these ones. And 21 is the largest. Which of the following is closest to the largest number you cannot buy? The closest to that is 20. So the answer is B. Okay, that was a difficult problem. Yeah. That's hard to think about like that, but that kind of question shows up on like the AMC and on the probe. So it's just good to have that kind of strategy in mind, where you make the whatever the smallest like pack is, you make that many columns, and then you just write down the first times that you can make like whatever mod that pack number, and then everything after that you'll be able to make. But yeah, anyway, that was problems 6 to 10, and I'll continue with 11 to 15.